All right, Physics 2. Welcome back to part 2 of Wednesday's lecture. So what I have left leading up to your exam is just a few more examples. Because these chapters tend to be more conceptual, I want to give you more time to just practice these concepts instead of covering quite as much as we could on this exam, since you will have the last part of chapter 19, chapter 20, chapter 21, and the first part of chapter 22. Okay, so another Faraday's law example. We have a solenoid with N equals 500 turns per meter, and current is increasing at a rate of 100 amps per second. The cross-sectional area of the solenoid is 4.02 centimeters squared, which is equal to 4.0 times 10 to the minus 4 meters squared. So we want to do a few things. We want to find the magnitude of the induced EMF in the wire loop outside the solenoid, and we want to find the magnitude of the induced electric field within the loop if its radius is 2.0 centimeters. So once again, we're dealing with a solenoid. We've got our magnetic field, and we have a wire loop around it for which the changing current is inducing a changing magnetic flux, which is generating EMF. So we've got this would be the magnetic field, and we have our radius and our curly electric field. All right, so that's the setup that we're looking at. So now let's start looking for the magnitude of the induced EMF and the electric field. So EMF is equal to minus the rate of change of the magnetic flux, which is equal to mu naught N A di dt, where N is equal to N over M. So EMF is equal to minus 4 pi times 10 to the minus 7, 500 per meter, times 4.0 times 10 to the minus 4 meters squared times 100 amps per second. That's which is the rate of change of current. So EMF is equal to minus 2.5 times 10 to the minus 6 volts. All right, so part B, we want to find the magnitude of the induced electric field within the loop, that loop, if its radius is 2.0 centimeters. So we're going to start with E dot dl is equal to EMF. We're going to go in a circle. And this is 2 pi r E, where 2 pi r is dl and E is the electric field. So E is equal to EMF over 2 pi r, which is equal to 2.5 times 10 to the minus 6 volts, divided by 2 pi 2.0 times 10 to the minus 2 meters. And the induced electric field is equal to 2.0 times 10 to the minus 4 volts per meter. All right, so hopefully you're starting to get the hang of how to play these games and manipulate these equations to find out what you need. So remember what these different integrals actually mean in terms of shapes and geometries. Okay, so next example, we have a solenoid. Excuse me. With 2,000 turns per meter, with current changing at a rate di dt is equal to 3.0 amps per second. The solenoid is 50 centimeters long and has a diameter of 3.0 centimeters. A small coil consisting of n equals 20 closely wrapped turns in a circle of diameter 1.0 centimeters is placed in the middle of the solenoid such that the plane of the coil is perpendicular to the central axis of the solenoid. And what we want to find is what is the EMF induced by the coil. All right, so, excuse me. How many of you yawned along with me? So the magnetic field of the solenoid is mu naught Ni. Magnetic flux is equal to mu naught N I pi d squared over 4 for each loop. EMF is equal to N times the change of magnetic flux with respect to time is equal to N mu naught N pi d squared over 4 di dt. EMF is equal to 20 times 4 pi times 10 to the minus 7 Tesla meters per second times 2,000 1 over meters times pi 0.01 meters squared over 4 times 3.0 amps per second. EMF is equal to 1.2 times 10 to the minus 5 volts. All right, so this wraps up part 2 of Wednesday's lecture leading up to the exam, which means you'll be responsible through 22.2 for your exam covering Faraday's law. And I will see you next time.